Hello, welcome to today's Further Maths Mechanics tutorial video where we're introducing the idea of elastic potential energy, which is the energy stored in an elastic string when you stretch it. So, how do we calculate elastic potential energy? Well, good news, it's a very simple formula. It's just lambda x squared divided by 2L, where L is the natural length of the string or spring, x is the amount the string has been stretched by, or, if it's a spring, potentially compressed by as well, and then lastly, we've got lambda, which is the modulus of elasticity. Things to bear in mind are the units for these things. Lambda is in newtons, and elastic potential energy, being energy, is in joules. But when it comes to L and X, it actually doesn't matter what unit of measurement for length you choose to use, as long as they are the same as each other. So L and X have to be both meters, or both centimeters, or whatever. Cool, and as it really is as simple as that, let's launch straight into an example. Part A, we're given a string that's got a natural length of 4, so L is equal to 4. It's stretched until it's got a new length of 7.5. Watch out in the wording there, they're saying the entire new length is 7.5, so that doesn't mean that X is 7.5, because that's just the extra amount it's been stretched by. So therefore, X is actually going to be 7.5 minus the 4 that it originally was, basically telling us that it's only an extra 3.5 meters in comparison to before. The string has a modulus of elasticity of 10, so therefore lambda is equal to 10, and therefore we can work out the elastic potential energy, which I'm going to lazily write as EPE, is going to equal 10 lots of x squared, so 3.5 squared, divided by 2L, so 2 times by 4 is what we're dividing by. And if you type that into a calculator, you will get an answer of 15.323 significant figures. And there you go, remember to put units as well. Part B, watch out for the wording again. So we've got a spring with a modulus of elasticity of 40, so therefore this time lambda is equal to 40. It's compressed by 0.2, so by saying those words, they're actually directly telling us x this time. So that's why you've got to be so careful when reading this stuff. And the elastic potential energy stored is 0.5 joules, and we've got to find the natural length. So therefore, we've got to set up an equation. We know that 40 times by 0.2 squared divided by two lots of our unknown natural length, which I'm going to call capital L, is therefore going to be that, and that's going to equal 0.5. So we've just got to rearrange this equation to find what L is. If we times both sides by 2L to eliminate the denominator, that will give us that 40 times by 0.2 squared is equal to just L, because you'd have 0.5 times by 2L, and then if you type that into a calculator, that's telling us that L is got to equal 1.6 meters. And we didn't have to do any rounding that time, so that is the final answer. So watch out with the wording there. But there's some extra things you've got to be aware of. The first situation is one that we've actually talked about before in a previous video. It's when you have an object attached midway along the string. In other words, not at either end of the string. In which case, treat the piece of string as two separate mini strings, one piece for either side of where the object was attached. However, it is worth noting, if you're lucky and the object was attached exactly halfway along the string and both halves of the string were stretched by equal amounts, you could still treat the string as one big string and that would get you the same answer. But if you want to be safe, treating as two separate mini strings is guaranteed to always work in those sorts of circumstances. But then the second thing is something we haven't talked about before, which is that unlike forces, when you're dealing with energy, you don't have to resolve it if the string is being held in a diagonal way, which actually makes stuff a lot easier conveniently. So let's take a look at an example involving that. We've got an elastic string with a natural length of 2.4, so therefore L is equal to 2.4. The two ends of the string are attached to the points A and B, which are 2.4 meters apart, so we have A and B there and there. And when the string is attached to those points, it's not being stretched at all at that point. The 2 points are the same height as each other as well, that's why I drew them horizontally from each other. A particle is attached to the midpoint of the string, and then the particle is pulled directly down by 0.5 meters. So that means the string was originally here, but then after attaching a particle midway along it, we're then pulling it down 0.5 meters, meaning the string will look something like this. The good news is, because the particle was attached exactly halfway along the string, and then the string was just pulled directly down, meaning both sides of the string are stretched in equal amounts, we could choose to treat the string as one big string, but for the purpose of this example, I'm going to treat it as two separate strings. So therefore, actually, the natural length of the string is going to be 1.2 for each half of the string. And then, to work out how much they've been stretched by, well, this is where the dimensions they gave us in the question are going to play a part. Because we know the original length between A and B was 2.4, but that means each half between A to the midpoint and from the midpoint to B is just 1.2 each. And then, we also know the height of this right-angled triangle we've created is 0.5. So therefore, we can work out the length of the diagonally stretched string by doing Pythagoras. So therefore, that will tell us that the new length of the string is going to be 1.2 squared plus 0.5 squared, then square rooted, which is 1.3. That means each half of the string is being stretched by 1.3 take away 1.2, so that means it's being stretched by 0.1 meters. And then we're told later on that the modulus of elasticity is 25 newtons, so we have that lambda is equal to 25. It's worth pointing out that although I am treating the string as two separate parts, effectively treating it as if it was cut in half, the modulus of elasticity stays as the same as the original string, because lambda, the modulus of elasticity, is almost just a rating for how stretchy the material the string or spring is made out of. So therefore, even if you're only taking a piece of the string, those material properties are still holding true for that particular piece of the bigger string or spring. So therefore, the elastic potential energy in each half of the string is going to equal 25 times by 0.1 squared, all divided by 2 times by 1.2. If you work that out, you will get 5/48. However, that's just the elastic potential energy stored in each half of those two mini strings. The total elastic potential energy is therefore overall going to be 5/48 times by 2, which will get you as a decimal 0.208 joules to 3 significant figures. Cool! That is the answer to that question, and that is all that I wanted to cover for today. However, we do need to know how to use elastic potential energy in the context of solving certain problems, and that's what we'll look at in our next further mechanics tutorial video. Stay tuned for that, and see you over there. Goodbye!